Alright, so we've looked at electron configurations and what's going on with them and where those electrons are in those orbitals and different levels that they're in. So we're going to kind of move on and kind of look at the wavelength of light and how we see light with what's going on with these electrons. But what I want you to have a basic understanding of is when you're looking at electron configurations, if I give you two electron configurations, if I say 1s2, 2s2, 2p5, and then I say 1s2, 2s2, 2p6. You're going to have to be able to look at these electrons and configurations and tell me which one you think is stable and which one you think is unstable. So if you take a look at those, I hope in your mind you can decipher the difference between those. The fact that this one right here is stable. And the reasoning is because it has a p orbital that's filled. P orbitals can hold 6 electrons. It has 6 in it. So the 2p5, remember that what that orbital, that last orbital looks like is this. There's 5 electrons in it. So with 5 electrons in there, it needs 1 more to fill it. So this is a very unstable electron configuration. This element is going to gain an electron in this position right here and be very reactive to gain that electron from another element. So this is going to be, if you know from physical science, those are nonmetals that gain electrons and they form ions. We're going to move into that in a couple of chapters, so having a basic understanding of that is very important. So we're going to move on today and we're going to talk about the quantum mechanical model and how that involves the study of light. So understanding the basic background behind light and what a light wave is, we're just going to kind of look at that briefly, and then we're going to get into how this kind of ties in with this chapter. So you got to know kind of what a wave looks like. So you've probably seen this diagram somewhere along the line. You got waves, very pretty waves. So you've got two things going on. You've got a distance between there and there, and there and there. So this one going here is the wavelength. And that is represented by lambda is the way you're going to see it. It's the distance between the crests of those waves. And then you've also got this one, which is amplitude. We're not going to talk about that one very much, but it just means how tall the wave is. From the height of it from 0 to where it crests. So how tall is that wave? Another function that kind of ties in with waves is frequency. This, for some reason, is represented by a V, and that's the Greek letter nu. So that is the number of waves that cycles to pass a given point. So you can have high frequency, you can have low frequency, and we're going to kind of talk about that. But hertz is the measurement that it's in. Hertz is just how many cycles of that wave pass per second. And that's all that really means. But whenever you see frequency, the measurement is going to be hertz. So here's kind of some examples. The wavelength and frequency are the two that we're going to kind of zone in and look at, but these two are inversely proportional. Now I know you've heard that term before. Inverses mean opposites. So when we're looking at light here, what it means is where I have a long wavelength, I have a low frequency. But on the other hand, where I have a short wavelength, I have a high frequency. So these over here on the left, those are going to be very slow moving, not very dangerous light waves. So we're looking at very low frequency, but there's very long wavelengths because there's not very many waves passing per second. On the other hand, the one over here, the waves are moving faster per second, so it is a higher frequency, and there's a shorter distance between those waves. So that's kind of, they can have the same amplitude, but if I have a shorter wavelength, I'm going to have higher frequency. Alright, so there's a formula that we can use, and we're going to use that probably in the next video to look at how we can calculate either the frequency or the wavelength. So we've got a formula. It is c, which is the speed of light. And the speed of light for you guys is always going to be a constant. It's going to be 3 times 10 to the 8th meters per second. Then you've got, this one is the wavelength, and this one is the frequency. So remember, wavelength is usually going to be measured in meters. Frequency is going to be measured in hertz. So there's the formula that we're going to use in a little bit. So we'll come back to this formula in a few minutes and we'll kind of calculate. We're either going to calculate the wavelength or the frequency. We'll have one of the variables, but we're always going to have the speed of light over here. That's always going to be 3 times 10 to the 8th meters per second. So looking at the wave model, we're going to see a picture in a little bit that has all these variables. So as we look at the whole spectrum of electromagnetic radiation, light waves are going to include radio waves, microwaves, infrared, visible light, and that's going to be important. That's the light that we see. That's the only part of the spectrum that we can see. Then you've got ultraviolet waves, X-rays, and then even gamma rays. So some of these are going to have higher frequencies. They're going to be more dangerous to us. The last bullet here is just kind of already what I've talked about. If you've got waves traveling in a vacuum, we're going to use a constant. The speed of light is always going to be 3 times 10 to the 8th meters per second. So we can take sunlight, and whenever we get back in class, I'm going to show you this. We can take a prism, or what's called a spectroscope, and we can put it up to the light, and we can break it up into the colors that we know. You guys may have learned a trick somewhere along the lines. It's called Roy G. Biv. Those are the colors of the rainbow. So we've got red, orange, yellow, green, blue, indigo, and violet. So we can put that spectroscope up to the light, and what it'll do, it will break it up into the different parts of light that we can see, because they all fall at a different wavelength. So red light has the longest wavelength. That's this one right here. So then violet on the other end is going to have the shortest wavelength, which would mean this would be the highest frequency. And then on the other end, red is going to have the lowest frequency and the longer wavelengths. So that might just be a test question, understanding that. So to see the picture of the entire electromagnetic radiation, that's what we're going to move on to. Here is the picture. So you can see the wavelengths right in this section right here. How when we're looking at radio waves or radar or microwaves, they're very long wavelengths, and that means low frequency over here. These are low frequency. And then over on the right, these are your higher frequencies. So as you move across this spectrum, the light waves get more dangerous. Now right smack in the middle, right here, that's where the visible light is. They kind of broke it up, and they showed how, red light over here is the lower energy, purple is the higher energy, meaning higher frequency. So when we move over here to gamma rays, that's where they get really dangerous. That's where the light waves have a very high frequency. X-rays are even in there too. That's why we don't try to get X-rays a lot, because they are dangerous, but every now and then we do have to have X-rays. UV light, we get that when we go out in the sun, but technically we should be putting sunscreen when we go out there. But those are just some of the forms of light that can be dangerous. UV, X-rays, gamma rays. Visible light, not really that dangerous. Even moving down over here, there used to be talk that microwaves were dangerous, but as you can see, the wavelengths are pretty low, or the wavelengths are long, and the frequency is pretty low, so they're not very dangerous. So this is just kind of an idea, and we're going to get into the next video how this kind of ties in and why it's important to understand light, because it is what is going on with these electrons. When they start moving and absorbing energy, it really is dealing with what's going on with light. So we'll get into that in the next video. We're going to go ahead and end this one right here. So answer your questions for your whisk, and you are done. Thank you.